Welcome back, Bulldogs. It's Monday, April 20th, and I hope you all had a wonderful spring break. In this lesson today, we are going to be working through a couple of things. The first thing that we're going to do is we are going to review factoring. I have a few practice problems for you to work through, and then we will check our answers together. The purpose of this is to help us remember all of the work we were doing in those first 3 weeks that we were at home before spring break, because we're going to use that idea of factoring in the coming weeks with what we're going to be covering next with quadratic equations. The second thing that we're going to do today is we're going to take a look at what the graphs of quadratic equations look like. We're going to work through an exercise that will help you graph quadratic equations, and we will take a look at some of the vocabulary associated with those graphs. Then we will summarize everything that we did and review. And the last thing that we will do is we will have some closure, get some practice, and get ourselves ready for Wednesday's lesson. All right, I think we're ready. Let's get started. Please access your guided notes worksheet in the lesson tab for today's lesson in Google Classroom. The first thing I'd like you to do is work through these 6 problems as a warm-up. You will be factoring each expression completely. As you do so, make sure you remember the strategies and shortcuts we discussed before spring break to help you out. For each problem, start by looking for common factors that might be able to be pulled out first. Ask yourself, is there a missing term, and would it help you to use a 0x term as a placeholder? Is the quadratic a difference of 2 squares? If it is, remember that you have a shortcut that you can use. You can always use area models and diamond problems to help you factor. Take a few minutes and work through these practice problems. When you are finished, resume this video and you can check your work with me. Now that you've had a chance to work through these practice problems, let's check your work. I'm going to talk through the main ideas of each problem and give you the final answer. If you have further questions, please consider dropping into one of my student support sessions this week. The schedule is posted in Google Classroom still, and these are awesome opportunities for us to work through problems like these in greater detail together. In this first problem, there is no common factor to be pulled out of each term, and there is no missing middle term. It's not a difference of 2 perfect squares, and so to factor it, we can just jump right into our normal methods of using an area model and a diamond problem. This expression factors to x minus 9 times x plus 4. In problem number 2, there is no common factor to be pulled out, but we are missing a middle term. If you would like, you could start by rewriting this expression with a 0x term as a placeholder. Then you could continue on with your area model and diamond problem to help you continue factoring. You might also notice, though, that this is a difference of 2 squares. 8 times 8 will give us 64, and x times x will give us x squared. That means we can apply our shortcut for factoring the difference of 2 squares, which is if we have a squared minus b squared, it factors into a minus b times a plus b, which means x squared minus 64 factors to x minus 8 times x plus 8. If you went through and used the area model and diamond problem with the 0x as a placeholder, you would end up in the same spot. So either method is valid here. For problem number 3, there is a common factor that we can pull out of each term. Each of these terms is divisible by 3 and also has an x to spare. So we are going to pull out a 3x from each term. If we do that, we're left with x squared minus 2x minus 15. And you can always check your work by mentally distributing the 3x through the parentheses and making sure you end up back where you started. Now what we want to do is take a look at what's in the parentheses and see if we can factor that some more. There's no missing middle term. It's not the difference of two squares. So we can jump right to the area model and diamond problem. And if you do that, you will find that the larger parenthesis factors to x minus 5 times x plus 3. So the expression 3x cubed minus 6x squared minus 45x has three factors: 3x, x minus 5, and x plus 3. In number 4, we don't have a common factor to pull out, but we are missing a middle term. So we could start by rewriting this as 4x squared plus 0x plus 1. If we take a look, both parts of the expression are perfect squares. 2x times 2x will give us 4x squared, and 1 times 1 will give us 1. So to start, it looks like we might have the difference of two squares, but the catch is that we're adding these two terms. We're not subtracting them. So it's not a difference of two squares. We can go ahead and try factoring using our area model and diamond problem, but what you will find is that this expression is not factorable. In the expression in problem number 5, both terms do share a common factor of 2. 2x squared is divisible by 2, as is 50. So we're going to pull out that common factor of 2 first, and we're left with x squared minus 25. We are missing a middle term, so to continue factoring x squared minus 25, we could add in a 0x term as a placeholder. You might also notice, though, that we are working with a difference of two squares again. X squared can be obtained by taking x times x, and 25 can be obtained by multiplying 5 times 5. And we are subtracting the 2, so it is a difference. This means that x squared minus 25 can easily factor to x minus 5 times x plus 5 using our shortcut for the difference of two squares. And of course, we still have the factor of 2 from the beginning that we pulled out. Once again, if you choose to use the shortcut for factoring the difference of two squares, that's fine. Or if you would prefer to add in the 0x term and use the area model and diamond problem, that's okay as well. In number 6, again, we have a common factor that we can pull out. Each of these terms is divisible by 2y. If we pull a 2y out of each term, we are left with x squared minus 6x plus 9. Now we need to check to see if what's left in the parentheses can be factored some more. It's not a difference of two squares. We do have a middle term, so we can skip right to using the area model and diamond problem. When you do that, you will find that what's remaining in the parentheses factors to x minus 3 times x minus 3. So the expression 2x squared y minus 12xy plus 18y factors into three quantities, 2y times x minus 3 times x minus 3, which can be simplified and written as 2y times x minus 3 quantity squared, because the first parenthesis and the second parenthesis are exactly the same. So for the next part of this lesson, I want you guys to go outside and get some fresh air. Grab a ball, could be a smaller one like this, or if you want to use a basketball, that's fine too. And you're going to take the ball and I want you to throw it up and catch it. As you're doing that, I want you to think about the distance the ball is away from your hand as it moves up in the air and travels back down towards your hand. Throw it up and catch it. We're going to assume that your hand is at the same height for the release. Let me try that again. As you release the ball and as you catch it, I want you to think about that height, and then I'm going to have you draw some graphs. Now that you've completed the activity, I want you to think about how the height of the ball above your hand changed as you threw it into the air and caught it again. I want you to think about this as you work through the problems on this page. You are going to draw a graph that represents the height of the ball above your hand as you throw it into the air and catch it again. And then you'll be answering some questions about the situation. When you are finished, start the video again, and I will discuss these questions with you. Okay, so hopefully you've had a chance now to work through the 6 questions on your notes worksheet about this situation. Remember, you were supposed to start by drawing a graph of the height of the ball above your hand versus time. And so I've done that here. This is my graph, okay? This is what's happening with the ball as it moves up into the air and then back down to my hand. All right, notice that the graph is curved, and we're going to talk about that a little bit later, why it would be curved versus a line straight up and straight down. Okay, but first I want to talk through some of the questions with you. First one was, what's the starting height of the ball? And remember, we're analyzing the path of the ball in terms of its height from your hand. So if the ball is standing here on my hand, if it's starting here, my starting height would be 0 right here, okay? Then as the ball moves through the air, when it gets up to the top, the height grows fast at first, and then it slows down until it gets up here, and it actually stops for a split second before starting to fall back down towards my hand, okay? What's slowing the ball down as it moves up in its path? Gravity is, right? And so because as it moves through time, because the growth of that height is constantly slowing, that's why we're forming a curved path, all right? So at the start, my height is 0 and my time is 0. Over here is my other x-intercept, and that is showing when the ball reaches my hand back again at the end. So my x-intercepts show when the ball is starting in my hand and when it returns back to my hand. My y-intercept shows my starting height, and my graph here has a maximum. This maximum shows me where my maximum height is and the time that it reaches that maximum height. And this point is called a vertex. Every quadratic graph has a vertex. Sometimes that vertex is a maximum, sometimes it's a minimum value. In this situation, we're reaching a maximum height, so we have a maximum value at our vertex. The vertex is going to be located right in between our 2 intercepts. Those distances are going to be the same away from that vertex. And this line, if you remember from chapter 2, is called your axis of symmetry. So what I'd like you to do right now is stop the video, and we'll continue with this lesson inside. To summarize the work that we did outside, if we were to sketch a graph representing the height of the ball, h of t, above our hand as we throw it into the air and catch it again, it would look like this. The height of the ball at the start, when it's resting in our hand, would be 0. The time at the start would also be 0, and that position is represented right here at our first x-intercept on the graph. As the ball travels through its path, the height starts off increasing quickly and then slowly slows down until it reaches the top of its path. Right here, our ball stops for a split second and then continues losing height more quickly as it reaches our hand. And again, this is due to gravity. Gravity slows the ascent of our ball as we throw it into the air, and then gravity increases the descent of our ball as it falls down towards our hand. We said that one of our x-intercepts is right here at the start when we first throw the ball into the air. The other x-intercept happens in this position when our ball falls back down and reaches our hand again. So these points tell us when the ball is in our hand. We are also asked to mark the y-intercept on our graph, which in this case also happens to be one of our x-intercepts. This point tells us the starting height of our ball. Our graph does have a maximum value right here. This tells us the maximum height of the ball and the time at which the ball reaches that maximum height. And on the graph of a quadratic function, we call this point the vertex. Through the vertex of every quadratic function is a line that we call the line of symmetry. Lines of symmetry split things into two equal parts. This vertex and this line of symmetry are the same distance away from each of the x-intercepts on our graph. In this case, since our vertex is a maximum point, it's telling us the maximum height or the maximum y value of this situation. The last question you're asked to answer is about the domain and range of our graph. Remember that the domain represents the x values we can use for a situation, and the range represents the y values that we can use for a situation. Sometimes our domain and range is very broad, but other times we have to cut it down to fit a specific situation. In this case, our domain is going to represent the x values or our time. Our time starts at 0 and continues until the ball reaches our hand again. So let's say it takes 2 seconds for the ball to be thrown up and then come back down into my hand. That would mean the domain in this case would be all x values between 0 and 2, because my time starts at 0 seconds and ends at 2 seconds. For the range, that's going to represent the y values that are being used in this situation. Well, in this situation, the very first y value is 0. When the ball is starting off in my hand before I throw it, it is at a height of 0 units above my hand. Let's say we're measuring the height in inches, and let's say I am throwing the ball up to a maximum height of 15 inches above my hand. Then my range would go from 0 inches above my hand all the way up to 15 inches, or my max height above my hand. To summarize the ideas from this lesson and the vocabulary, the graph of a quadratic equation is in the shape of a parabola. Parabolas are U-shaped and can either be right side up or upside down. The roots of a quadratic equation are the x-intercepts of the graph. The roots of a quadratic function are the x values when the function is equal to 0. In other words, it's the x value when y is equal to 0. The y-intercept is the place where the function crosses the y-axis. When the graph crosses the y-axis, the x value will equal to 0. The vertex is the maximum or minimum point of the function. The first graph here has a minimum value, and the second graph has a maximum value. The axis of symmetry is a vertical line that passes through the vertex of every parabola. This axis of symmetry splits the graph of the quadratic function into two equal parts. To help you synthesize the ideas from today's lesson and set the foundation for Wednesday's lesson, I'd like you to answer the 3 questions on this page. Wednesday's lesson will start with us discussing these questions, and then we will move on to see how factoring can help us find the roots of a quadratic function.